seen the definitions that we need. And now I think the best way to continue is just to go on with some examples. So, usual thing, we have a series. We want to test for convergence or divergence. But now we're going to actually add an extra layer of thinking here. Does the series absolutely converge? Or do we only have conditional convergence? Or heck, do we even have divergence? Usual rules apply. So let's start off with this one here. We got an easy looking series here. Let's look at the first few terms. We have 3/5 minus 3/6 plus 3/7 minus 3/8. Okay, and we're asking, does the series converge absolutely, conditionally, or does it diverge? And you can see that this is an alternating series. We have plus, minus, plus, minus. And so let's go ahead and try to put this compactly in summation notation. That way we can identify our helper sequence Bn. So we can see here that it looks like all my numerators will have 3s and my denominators, well, they're just going up by 1 each time. 5, 6, 7, 8. So it stands to reason that this sum here that we're looking at, I can start the sum at 1 if I wanted to, or 0, doesn't really matter, or to make it even easier, I can even start the sum at 5. It doesn't even matter. So I want -1 to some power, be it n plus 1, n or n minus 1, but we have to make sure that we have the correct signs. So the odd number terms, the first and the third and the fifth and so on, the odd number terms get a plus sign, the even number terms get a minus sign. So just by thinking here, if I start the sum at 1, my power on -1 should be n minus 1, or n plus 1, same thing. Now let's think about the rest, okay? This is actually going to be what our helper sequence is. We're going to have 3 over, well, in order for that first term to have 5 as a denominator, I need n plus 4. Okay, and then we can see here 2 will give us will give us 6, okay, 3 will give us 7, and so on. So that's our series. And now let's identify our helper sequence, okay, that we need for the alternating series test, because this is indeed an alternating series. So the helper sequence here is Bn equals 3 over n plus 4. Now, this is certainly a positive sequence, okay? So Bn is positive. We know that, okay? Positive number divided by a positive number is positive, okay? Easy enough to think about that. So we have a check there. But now for decreasing, okay? We need to check for decreasing. There are many ways you can check this. You can take the rotos if you want, use some inequalities. And in fact, I think here the inequality actually is very much the easiest way to go about this. Okay, so let's go ahead and show this using inequalities here. So we know, let's assume, say, n is smaller than m, okay? Now, if you remember from our comparison test video, right, whenever I take reciprocals, a common operation I can do, when I take reciprocals, I reverse the direction of the inequality. So if I take reciprocals here, 1 over n is now bigger than 1 over m, okay? Now I can multiply by 3, and 3 over n is bigger than 3 over m. So, and doing an appropriate index shift here, if you replace n with n plus 4, and likewise m with m plus 4, okay, so we have that Bn is decreasing. Okay, that's just using inequalities there. One way you can do that there. And now what's the last part that we need for the alternating series test? We need to make sure that this thing has limit 0. And that's very much clear here, okay? So the limit as n approaches infinity of Bn, okay, we have the limit as n approaches infinity of 3 over n plus 4, basic calculus 1 limits. That limit is 0. So we have a helper sequence that is positive, decreasing with limit 0. So by the alternating series test, okay, which I'll abbreviate to AST, okay, for the remainder of this video. By the AST, the sum, the series, is convergent. Okay, so we answered the first part here. We now know that the series is convergent, but we want to take this a step further. Does the sum converge? Absolutely. So to test for absolute convergence, we're going to go ahead and just take absolute values. Okay. So now we need to test for absolute convergence. So to see if this thing converges absolutely, we're going to look at the sum of the absolute values here. So we're just going to put in absolute value signs here. So we had, what was it? -1 to the n minus 1, okay, times 3 over n plus 4. Now, when I take absolute values, I'm just changing anything with a minus sign to a plus, and so I'm just getting rid of the alternating bit. And what that really means here is I'm just looking at my helper sequence. So we have the sum from n equals 1 to infinity of 3 over n plus 4. But you should know that this thing almost looks like a harmonic series because it is a subset of the harmonic series, okay? This diverges, okay, by the p-test. Because in this case here, p is equal to 1. You can also check this by the integral test, since we already have shown that this thing is decreasing. You can show it by the integral test. You can use limit comparison, direct comparison. You can use whatever test you want here, but here it looks so much like a harmonic series, we may as well just use it. So this sum does not converge absolutely because the sum of absolute values does not converge. So we say the original series, let's go ahead and fix that. The original series converges conditionally. Okay, the original series converges conditionally. And what does conditional convergence mean again? It means that the original sum is convergent, perhaps by the alternating series test or whatever theorem you want to use, but the modified series with absolute values does not converge. And so you can think about the condition here is that the terms have to switch sign as plus minus plus minus. Okay. So let's go ahead and look at another one here. Again, same kind of thing. Absolutely convergent, conditionally convergent, or divergent. And here we already have the sum already written out for us using the sigma notation. Okay, -1 to the n times n over n squared plus 1. Okay, so this is indeed an alternating series. Let's go ahead and try to identify what our helper sequence would be. And here, just as before, we're going to go ahead and look at the not alternating bit. So everything I'm putting in yellow, our helper sequence here, Bn, is n over n squared plus 1. Okay, n over n squared plus 1. Now we need to check, is this a positive sequence? Is it decreasing? And does it have limit 0? Okay, this is certainly positive because n is positive, n squared plus 1 is certainly positive, and positive divided by a positive is a positive. And I'm saying positive a lot because I want us to keep positive. Okay, so Bn is positive. Okay, we know that. That's a check. But now to check for decreasing, again, you can use various things, okay? Inequalities, you can take a derivative if you want to. All right, let's go ahead and look at this here. So Bn is decreasing. Okay, we'll do that off on the side here. And I'm actually going to go ahead and approach this in the following manner, okay? So we know that let's go ahead and take a look at this here. We know, let's suppose, as before, n is smaller than m, okay? So I'm increasing, okay, in my index, okay? M is further away in the sum than m, okay? Then I can certainly say the following, okay? Then n squared plus 1 is less than m squared plus 1. Okay. Well, if n is smaller than m, then n squared is smaller than m squared, then I can add 1. I preserve the inequality. Okay, now we're going to go ahead and take reciprocals here. We have 1 over n squared plus 1 is now bigger than 1 over m squared plus 1. Okay. So now we have this inequality. Okay. It stands to reason that we think that this thing is decreasing. Okay. We can kind of check it just by experimenting, but we have to verify. Okay. We have to actually show, through reason that this thing is decreasing. And you can't just do that by looking at the first 4 or 5 terms. Okay. Maybe something happens later on. You need to verify this for every single thing. All right. Well, now let's go ahead and write out the two inequalities that I have here, okay? We have n is smaller than m, and then if I flip this over, I have 1 over n squared, rather m squared plus 1 is smaller than 1 over n squared plus 1. Okay, that was not a typo. Okay, I want to write this in the same direction because now when I multiply down through, okay, if I multiply the inequalities together, okay, left hand side times left hand side, I get n over m squared plus 1 is smaller than m over n squared plus 1. Okay. Now, this looks a little strange, don't it? But remember, n is smaller than m, okay? N is smaller than m. So I can now certainly say here that n over n squared plus m squared plus 1 is smaller than m over m squared plus 1. Okay, and I can get a similar inequality. Okay. I can get a similar inequality here if I multiply by the inequality n is bigger than 1, because, well, the sum starts at 1 and n can only be 1 or larger. I obtain the following, that n over n squared plus 1 is bigger than 1 over m squared plus 1. And I can conclude that n over n squared plus 1 is bigger than m over n squared plus 1. Okay? And so, through all that reasoning, we have that Bn is decreasing. Okay, so that's a bit of work. Again, you can go ahead and use derivatives if you like. I think the derivative approach may be a little easier. Okay, but remember, as before with the direct comparison test, you got to know how to use those inequalities. All right, let's go ahead and now check the easiest part here. Bn goes to 0. Well, it certainly does, right? You just take the limit there, okay? It's bottom heavy. The denominator is going to go faster, okay, at infinity, because, let's look at it here. The limit then goes to infinity of n over n squared plus 1. You can do the usual calculus 1 trick, get a limit of 0. So now, by the alternating series test, okay, the sum converges. And now we're going to ask a question of absolute convergence. And so for absolute convergence, again, we take the sum of the absolute values, which really means we discard the alternating bit here. So I'll write this step in one more time, minus 1 to the n times n over n squared plus 1. Okay, and the absolute value will toss away the alternating bit. So we have this sum here, the sum from n equals 1 to infinity of n over n squared plus 1. And we've seen this sum a few times already, okay, throughout this chapter. Okay, some ways you can attack this, okay, you can perhaps attack this with the integral test, perhaps limit comparison, direct comparison, okay, lots of ways you can do this, okay, and in fact, we can already use the integral test since we've already shown that this thing is decreasing eventually, okay, so let's look at the integral test, although, of course, the limit comparison test would also work here as well, just compare against anything like 1 over n. Okay, so if I do the integral test here, okay, and I'll skip some of the details here, okay, you can see that you can do a u substitution here, or use a trig sub, because you got a square plus 1 in the denominator, okay, you can see here that we'll get 1/2 log of absolute x squared plus 1, evaluated between infinity and 1 in limit, but then you'll see that this limit ends up being infinity, okay, so the integral diverges. And what does that mean? That means the corresponding sum does not converge. So the series, the original series, is conditionally convergent. Okay, so whenever we test for the absolute convergence, we may have to use something new. Okay, absolute convergence is not a test, but rather just another statement that we're trying to show here. One more time, another sum that we probably have seen a variant of so far. Minus 1 to the n minus 1 times log n over n. And so what is our helper sequence here? Well, it's just log n over n. We've seen that plenty of times here. Okay, let's ask ourselves these questions. Is this positive? Okay, well, log is positive for n bigger than 1, so certainly bn is positive. Okay, we know this. Put a check there. And for bn decreasing, okay, I'll go ahead and use derivatives here. I think it's a little easier to use derivatives here. So for bn decreasing, okay, we'll look at f of x equals log x over x. I'll extend this to a continuous function. And when I take derivatives here, just using the quotient rule, okay, I won't really go through the whole details here. If I use the quotient rule, bottom times the derivative of the top, okay, so we have x times 1 over x minus top times the derivative of the bottom. We got a log x there, all over the bottom squared. We get 1 minus log x over x squared, okay, and we want to see where this thing is decreasing. So we want to see where this is negative. And in fact, it can be shown that this is negative for x greater than e. Okay, log of e is 1, and then for anything bigger than e, the log of x will end up being a positive number bigger than 1, okay, and 1 minus something bigger than 1 is going to be negative. So this is decreasing eventually, okay, so that's a check there, okay, and a remark here again, f is decreasing. All right, and does it have limit 0? Well, we'll just go ahead and take a look at that. So the limit here is n goes to infinity of log n over n. Okay, if we plugged in infinity, we get an infinity over infinity. So we use L'Hopital's rule. Okay, so now we're looking at the limit as n goes to infinity of 1 over n, the derivative of log n, over 1. And this is 0. And so our helper sequence has limit 0. Again, by the alternating series test, because we have all the 3 of those conditions satisfied, the sum converges. Okay, so the sum is convergence, but now we need to ask the question, does it converge absolutely? Okay, so for absolute convergence, we look at the sum of the absolute values. So we're going to go ahead and drop that there. So we're going to consider this sum here. We have log n over n going from 1 to infinity. Okay, and again, remember that I'm just dropping the negative parts there, so we're just keeping the helper sequence there. And this we've seen before, okay? In fact, we're going to use the integral test here because we already know that this thing is decreasing, okay? So we're going to go ahead and use the integral test. So when we use the integral test, okay, I'll go ahead and do the integral from, well, it suffices to really just look at this on the same kind of range here, 1 to infinity, though you could do this from, like, say, 3 to infinity, if you remember from the integral test exercises. But I'll be a little loose here. We're going to integrate log x over x dx here. Okay, and this is just a simple u substitution. U equals log of x. And so du is 1 over x dx. Okay, so remember our improper integral techniques. So we're going to take the limit here as t goes to infinity of this integral. Okay, when x is 1, u is 0. And when, let's see here, as t goes to infinity, u goes to infinity. So we'll have t to infinity, okay, up there. And now what do we have in the integrand? We have u du, an easy enough thing to look at an antiderivative, 1/2 u squared. And you should be able to see that this thing goes to infinity. So this integral diverges, okay? So the integral diverges. So the sum conditionally converges. Okay, so if the sum of absolute values does not converge, but the original series does converge, again, we say that it is a conditionally convergent sum. Okay, I think we got a couple more here. Okay, we want to see again if this one is absolutely convergent or not. Okay. Now, this is not an example of an alternating series by our definition here. Our alternating series has to have a plus minus plus minus plus minus kind of thing. Okay. And here we kind of do have that, but every time, every term, the terms don't flip, right? We'll have some that are plus in a string of minuses, some that are plus in a string of minuses. And so we have to resort to something else here. And in fact, what we're going to do is actually use the power of the direct comparison test. Okay. Now, why am I talking about the direct comparison test here? Okay, well, this is not an alternating series, so this is not alternating by definition because it's not -1 to a power times stuff here. And so let's go ahead and use the DCT. And what I'm going to do is I'm actually just going to go ahead and test straight out for absolute convergence here. Okay, you'll kind of see why I'm doing this here. So we'll make a note here. Okay, if we remember our fundamental inequality here, okay, sine of x is less than or equal to 1 for all x. And so, how do we use that? We note that our summands here, sine of 2n over n squared, this is going to be less than or equal to, well, here the angle is not just an x, but it's 2 times n. But it's the sine of something. And the sine of anything is no bigger than 1 in absolute value. So I'm going to replace the numerator there by a 1, and the denominator I'm going to keep as n squared. Now you might ask, where did the absolute values go? Well, absolute value of a positive number is still a positive number, and n squared is positive. So I can just keep that there. But I can replace the numerator by 1 in the absolute value. Okay? Now, think about this. Okay? By the p-test, okay, by the p-series test, this sum here, the sum of all the squares of reciprocals, 1 over n squared, this is convergent as p is bigger than 1. Okay? And again, I'll probably mention this fun fact here. That sum right there is equal to pi squared over 6. You don't need to know that, but just a little fun fact there so that you can be convinced that there is an actual number attached to it. Okay? So by the p-test, that thing is convergent. Okay? And so by the direct comparison test, we have the following. Okay? We have that our original sum, sine of 2n over n squared, okay, summing from n equals 1 to infinity, converges. But not only does it converge, but it converges absolutely. Okay? Now, remember what the direct comparison test says. If I can bound my summands by a sequence from above whose sum is convergent, then the smaller one must converge as well. Okay? Here, we also use a fact here. I probably just waited in passing here, but we use a fact here, which I'll just mention here, that x is always less than or equal to its absolute value. Okay? And so we have the following string of inequalities here. We have our original summand, sine of 2n over n squared. That's going to be less than or equal to its absolute value. And by the above, we know that this is less than or equal to 1 over n squared. Okay, and then by the direct comparison test, I almost said dominated convergence theorem. That's another DCT that's in math there. Okay, by the direct comparison test, okay, because 1 over n squared is a summable sequence, so too are the smaller ones. Okay, now let's look at this one here. Cosine squared of 1 over n. Okay, again, this is not one where we can just go ahead and use the alternating series test because I don't have a -1 to n or an n plus 1 power or something like that. But take a look here, right? I have summing the squares of cosines. Well, the squares are all positive. So this isn't even an alternating sequence. We don't even have an alternating series here. But something looks really fishy here. I'm just going to go ahead and take a look at the limit here, okay? Let's look at the limit of the terms here. So the limit, as n approaches infinity, of cosine squared of 1 over n. Okay, now we're going to go ahead and use a result here. I won't prove it. But that says if I have a composition of continuous functions, I can pass the limits through, okay? So I can pass the limit through into the cosine. So we have the cosine square of the limit as n goes to infinity of 1 over n. And certainly 1 over n goes to 0. So we have cosine squared of 0, which is 1. So my terms don't get small. They actually peter out at 1. We have the divergence test, okay? So by the nth term test, so by the divergence test, okay? So what do we just show? Cosine squared of 1 over n does not go to 0. The sum diverges. And that's it. If the sum diverges, there's nothing else we can say. It just diverges. Okay, so we saw some pretty cool applications here, right? We saw how to handle alternating series, some of these things with sines and cosines, and you see that you have to work in tandem with some of the other tests that you have already used. Okay, this is going to be a recurring theme, especially when you have alternating series or series where the signs aren't all the same. Okay, you have to first establish convergence of the original sum, then you might be asked about absolute convergence, and now you just use something else in your toolbox, say like the direct comparison test, limit comparison, the integral test, this p test, the let's see, the divergence test, or something that we'll learn in the next video, the ratio or the root test. And for that one, well, you'll have to see me in the next one.